Greetings and welcome. Today we're talking about our second type of conic section, which is called an ellipse. So ellipses is plural of ellipse, all right, just so you know, right? Single word there, right? And ellipses are kind of like circles, but that have been elongated in one direction. Technically, a circle can be viewed as a type of an ellipse, right? Kind of like how a square is a rectangle, but not all rectangles are squares. Circles are ellipses, but ellipses are not necessarily circles. So the common word that I don't know if it truly fits it would be like oval, all right? But so you can kind of have that in your thoughts. I'm not going to leave that written there just because we're calling them ellipses, friends. So let's talk about what the definition of an ellipse is. All right, so an ellipse is the set of all points right? And anytime I'm talking about set of all points, that's the same as a locus. I could call it the locus of all points on the plane, or in the plane. The sum of whose distances, man, this is crazy. From two fixed points called foci. All right, so it's kind of like instead of a center, it has two centers. I think that's actually technically pronounced foci. I'll probably call it foci, fuki. I don't know, all sorts of weird. Foci. It's the plural of focus. Okay. So like that's what's interesting is the company Ford actually had to decide what you call multiple Ford Focus vehicles. Like, do you just call it, hey, I've got a couple of foci parked in the garage? Or do you call them Ford Focuses? Yeah, but foci or foci is technically the plural of focus. So two foci or foci is constant. All right, so this is related to distance. It's related to all sorts of stuff. The general idea, I think I'll draw a picture for us. Okay, the general idea is this. So imagine this is just going to be a rough picture. I'm going to pick 2 points. All right, so let's say I've got this point here and this point here. All right, so here's like focus 1 and focus 2. All right, and I've got some set length. All right, so imagine I had like a string hanging between these, right? And I'm going to pull this string tight and plot a point and then draw all points in which that string is tight. So what that would look like is, you know, I might have a point here. So this string length is the same, right? So I'd have that point plotted. Maybe up here, the string length is the same, right? Or over here, the string length is the same. Over here, right, the string length would be really long there and really short there. But the overall length of that is constant. So I end up getting like an interesting shape, right? That is like an oval. It's a stretched out circle. And it's symmetric in many capacities and things like that. Let me show you a this sketch here. So here's this little lower corner here. This is from Algebra in Motion, or Calculus in Motion is the lady's website. So here's like the idea of if I have a pencil, that blue line is a set fixed length, and if I was to draw around, pulling that string tight, that's the shape that I would get, right? And you can even see that if I was to shorten the length, the oval would actually have really, the foci would be really close to the edges, right? like that. If I drag the foci closer together, it becomes more of a circular shape, right? So it's less apparent that it's been stretched out in one direction. And if the foci are in fact exactly the same, then it'll in fact be a true circle. So you can think of a circle as just being, two foci that are identical. So you can kind of see, right, this idea here as well. So the individual lengths from either foci to the point are changing, but the sum of the two lengths is constant, right? So you can kind of see that going on there. All right, there, go away, stop. So that's the idea behind it. Now there's a whole bunch of additional things going on that I'm going to label with vocabulary before we even get to the equation. So I might actually try to draw a better sketch first of all. Here we go. Actually, you know what? I'm going to cheat and use my circle tool, or elliptical tool thing, I guess technically. All right, I guess I get to start at the center. Just so you draw a really big sketch of some sort of ellipse that's horizontally oriented, like so. Okay. And so let's label some points. So the center is still called the center, all right? And the center is going to be h comma k. Let's see, so center h comma k. I'm going to have some other points. The longest distance, all right, I'll have points here and here. These are called vertices, okay? So I could call that V1, V2, and technically up and down, the minimal distance, the shortest of the radii possible, would be, other vertices as well. So those are all just called vertices, right? So there's a longest radius, I guess, and there's a short radius, if you want to think about it that way. It's not quite the case, but that's fine. And then the foci are somewhere between your center and your longest, your furthest away points. So here would be like foci 1, foci 2. All right. Now, so let's talk about some of these distances. So the distance from here to here is called A. All right. And that's going to show up in our equations. The distance from here to here is called B. And the distance from your foci, and it's symmetric fortunately, will be called C. All right, so far, does it make sense? I want to point out that there is actually going to be somewhat of a Pythagorean relationship between A, B, and C. However, I want to point out that C is shorter than A, right? Here's another length of C, and it's shorter than the length of A, okay? Some names of things. The longest distance across is called the major axis. So there's a lot of vocab here. The shortest distance across is called the, you probably could guess it, minor axis. Okay, and it turns out A, what do you think A is compared to the length of the major axis? Exactly half of it. So A is also referred to as the length of the semi-major axis. All right, and B is going to be referred to as the length of the semi-minor axis. Sorry. So there's a lot of stuff going on here, as you can clearly see. All right, so I think I've hit most of all of that. Good, 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 good. And I think I want to show you the derivation for the formula. But we're not going to do it. Let's see. Oh, it's got the blurries here. This is from our text, page 633. This is not my work, so you're just checking this out here. So basically what they say is that I've got, the distance from F1 and the distance of F2, those add together to be a set distance the whole time, which happens to be the length of the major axis, is that overall thing. So they end up kind of manipulating some of this stuff. So they bring the x side, one of these over here, and isolate a radical, square both sides, which that's from like Math 3 stuff back when, actually I'm going to be teaching that this week to Math 3. And then they simplify, they isolate another radical, square both sides again, and they simplify, they pull everything together, and they end up getting this nice little equation here. Okay? So that's kind of the derivation for the formula. I don't expect you to know it, but I do expect you to know the equation. So the equation for a horizontal ellipse, all right, horizontally oriented ellipse. So this is a standard form. Of the equation of the ellipse. All right, so for horizontally oriented ones, we'll have the following. It'll be x minus h all squared over a squared, and then that fraction is added to y minus k all squared over b squared, and this is always equal to 1. And I just want to point out that if a and b were equal, that would have just been like r squared in the denominator, and you could multiply both sides by r squared. You'd get the equation of a circle. All right, so it's really similar. Now, there's a side fact that c squared is equal to a squared minus b squared. So if you had to find out the location of the foci, and you know what a and b are, you can find c. All right, so let me give you some facts about this particular version. So this is horizontally oriented. Meaning it's stretched out kind of like this one. It's wider than it is tall, right? That's what I mean by horizontally oriented. You know it's horizontally oriented because a squared is bigger than b squared. All right, so whichever fraction has your larger denominator, notice that the a squared is under the x, so therefore it's horizontal. If my larger denominator was under the y, then it would have been vertically oriented. Okay? Let's see, our center would be at h comma k. Our foci are always along the major axis, so our foci are going to be, and in this case, since it's horizontally oriented, the major axis is that way, you're just going to add or subtract whatever c is to the x coordinate of the focus, to the center, and the y coordinate would stay the same. So just looking back up at this picture, if this is hk, this point would have been h plus c comma k, right? Don't draw that in. And this would have been h minus c comma k, right? Because I've subtracted c from the x or added c to the x, right? So that's what that's referring to. I don't actually recommend you memorize this. I'd rather you kind of imagine the picture and be like, okay, I want to add c or subtract c to the x coordinate. And that's how I kind of do things. The major axis is going to be the equation y equals k. So that's the equation of a horizontal line. So don't just say the major axis is the number k, because it's not. It's an equation, right, representing, you know, all points that kind of are on that horizontal line. The minor axis is going to be x equals h. So it's the vertical line that passes through the x coordinate of the center. Now your vertices, you'll have your major axis vertices you could refer to, right? The major axis are the ones furthest from the center. The minor axis vertices, they're not actually labeled V1 through V4. I was just kind of indicating that those are all vertices there. So for the major axis ones, it would kind of be like this, except instead of adding and subtracting c, what should I add and subtract, do you think? How would I find the coordinates of this point? What could I add to the center? Yeah, add a, and what should I add a to, the h or the k? The h, because this is horizontally oriented, right? So h plus or minus a comma k. Once you know those numbers, you can just kind of plug them in and figure out what the vertices are. The minor axis vertices, I'm going to add and subtract b to the k coordinate, right? So it'll be h comma k plus or minus b, right? And let's see. So that's all of the facts for the horizontally oriented one. And I'm just going to quickly go through a vertically oriented one. It would look like this: x minus h squared over b squared, b is the smaller one, plus y minus k squared over a squared equals 1. And our little fake Pythagorean theorem thing is still true. That c squared is equal to a squared minus b squared. So b is still the smaller one. And this one would be vertically oriented. The center is still h comma k. The foci always are along the major axis, which is now vertical. So it'd be h comma k plus or minus c. And you'll see that kind of things just flip-flop around here. The major axis is now going to be a vertical line, right? So that's going to be x equals h. The minor axis is now a horizontal line, so that's y equals k. And then the vertices. So if this is a vertically oriented ellipse, the major axis vertices would be h comma k plus or minus a. So this time I add the larger radius to the y coordinate and the smaller radius to the x coordinate. So there's a lot going on with these, but as long as you kind of keep track of everything, it's not terrible. It's okay. It'll work out. It is terrible? Oh, okay, I'm sorry. You can down-like this video if you want, but I'll know that it's because you don't like ellipses and not because I didn't present it in an awesome way. Actually, let me just draw a little picture of what I mean by a vertically oriented ellipse, right? So this one's like that, right? So then I'd have A would be this distance in this one, and B would be this distance, right? And then C would be the distance to a foci. Right, so that's what I mean by vertically oriented, just so you're aware. It looks like some dinosaur egg that's cracking open. Come on, little one, come on. This quote from Jurassic Park.
Oh, I know.
Of course, when he's got like the little robotic raptor coming out of the egg. It's a pretty good looking raptor for back in the day. So okay, let's see if we could do one of these. Let's graph an ellipse. And this might be all we get done today, but that's fine. We'll do our best. A lot of this behaves very similarly to circles. Actually, I might do 2 examples today. The second example you guys will probably leave for because you have to head out, but I'm going to keep recording for all of our internet friends. So let's graph the following. What if I've got x plus 4 all squared over 9 plus y minus 3 all squared over 25 equals 1. Okay, so here's our equation. So let's see, what facts can I gather? Could someone tell me what the center is? -4, 3. So the opposite factor of circles still applies for that, so that's cool. Could anyone tell me what a is equal to? Now, a squared, rather, is always the larger of the 2 denominators. So this is a squared. So a is going to be the square root of 25, which is 5. Okay? And then b is going to be the square root of 9, the smaller of the 2 denominators, right? So b is 3. So even with this information, I actually have enough to graph it. I could plot that point. Oh wait, I have to figure out which way this is oriented, which direction. Let's see, the larger denominator's under the y, so it's a vertically oriented ellipse. And even though I don't technically need the foci to graph it with this information, let's find out what would c equal. All right, so let's see. I know that c squared is equal to a squared minus b squared. So that means c squared is equal to, wrong color. There we go. So c squared is equal to a squared. I don't technically have to plug in 5 and square it. I know a squared is that denominator. I know b squared is that denominator. So I could just write 25 minus 9. So c squared is equal to what, 16? And then I could root, and I'd get c is equal to 4. Right? So that's c. So then my question is, let's figure out what are the vertices and what are the foci. So for the vertices, I would add and subtract 5 to which coordinate of my center for a vertically oriented ellipse? What do you think? Yeah, the second coordinate because it's vertical. So one of the vertices would be -4, comma 3 plus or minus 5. So 3 plus 5 is 8. 3 minus 5 is -2. Right? You guys can actually head out now. I'm just going to keep going so you can pack up. Just try to do it quietly. And then shut the door when you leave so I don't get all the noise in the hallway. So then the minor axis vertices, I'd add and subtract 3 to the x coordinate. So -4 plus 3 is -1. And -4 minus 3 is -7.
All students should be leaving their block on class with a break. Break will end in 8 minutes at 9:28.
And then we'll have, let's see, vertices and foci. So I add and subtract c to the y coordinate since it's vertical. So -4, comma 3 plus 4 is 7, and -4, comma,
Please report to your class meeting in 8 minutes.
that's right. 3 minus 4 is -1. So there's all my foci stuff. Let's actually now give this a graph. Let's see, I'm going to get rid of this and just get a little grid here.
All your class meetings are
Here I'm recording right now, still, because I'm all out of time. I know, it's crazy. Class meetings will be in here though. Let's see. So for this ellipse, we're going to have.
Don't we have breakers?
We're going to have the following. So let's paste this here. Bam. And plot the center is at -4, 3. Let's see, did I give myself enough room? I think so. -4 up 3 is right here, is my center. Vertices are at up 5, down 5. So up 5, 1, 2, 3, 4, 5. So there's the -4, 8 that we had earlier. And -4, down 5. So that's at -2 right there. And then I had B was equal to 3, so I'd go over here and over here. And I can actually draw my ellipse kind of one quadrant at a time, like so. Like so. And the foci, because I should actually list where they are going to be 4 units up. So that happens to be right there, and 4 units down, which happens to be right there. So there's a sketch of my ellipse based off of this graph. I think this will end up being the last example we do today. So thanks for watching, Internet friends. We'll talk to you later. Bye-bye.